So this is a short PowerPoint, just covering small angle approximations. There's a starter here for you to have a go at based on what I've covered in a previous PowerPoint, which is finding the area of a segment. So have a go at this and press pause, and then on the next slide then I'm going to show you the mark scheme so you can check your answer. So here's the mark scheme. I'm not going to go through it, but it's just there for you to check your starter question. Okay, so small angle approximations then. This is covered in page 11 of your booklet. If you wanted to approximate what sine of theta was equal to for a very small value of theta, then you could look at the sine graph. So if you have a look at this picture on the left-hand side of the screen, this shows the sine graph, well, just going from minus 180 up to positive 180. But as we zoom into very, very small values of theta, so along the x-axis here, very small values, so like 1 degree, 2 degrees, 3 degrees, that sort of thing. If you look at what the graph there, it actually looks a bit like a straight line. And the best way I think to do this would be to use a graphing tool like, for example, Desmos. It's the one that I usually use. If you go onto the internet and you go onto the website called Desmos, you can type in the graph y equals sine of x. And then if you zoom right in on the graph, so you can pinch the screen, if you've got a touch screen, you can zoom right in on the graph. When you zoom right in, and you go really, really close to the origin, you'll notice that the graph looks almost like a straight line. Now that straight line there is the line y equals x, or in this question we're working in terms of theta, so it would be y equals theta. So as the theta value gets very, very small, sine of theta, the graph of sine of theta, is almost identical to the line y equals theta, which is why sine of theta is approximately equal to theta, very small angles. I'm going to jump across now to the tan graph, and we'll come back to sine in a minute. So something similar happened to the tan graph. So if you type in on Desmos y equals tan of x, well, this one's using theta, so y equals tan of theta. If you zoom right in on the graph, to very, very close to the origin, where really, really small angles, really small theta values can be seen, you'll notice that the tan graph, when you zoom right in, becomes almost like a straight line. And that straight line again is the graph y equals x, or y equals theta if you're using theta instead of x. So the approximation for tan of theta is again just theta. The cos graph is a little bit different. So in this picture here, you can see that in black, you've got the cos graph. When you zoom right in on the cos graph, it doesn't look like a straight line. The cos graph, when you zoom in to the origin, still is a curve. The best fit for this curve, well, it looks a little bit like a quadratic, doesn't it? But it looks like an upside down quadratic. So we're thinking something to do with x squared, probably with a minus in front of it. So minus x squared, the negative quadratic. But it doesn't go through the origin, it goes through this point here, which is 0, 1. So it looks like a minus x squared graph, but that's been moved up 1. But if you on Desmos put that graph in next to the cos graph, you'll find that they're quite close, but not perfect. To make the approximation even better, if we divide that by 2, that minus x squared, it stretches the quadratic curve and it moves it a little bit closer to the cos graph. So you can see here in red, there's the graph 1 minus theta squared over 2, and that curve is actually very close to the cos curve, especially when you zoom right in towards the origin. So that's our approximation for cos of theta. It's approximately equal to 1 minus theta squared over 2. Now those three facts are not in the formula booklet, so you need to try and memorise them. This is a topic that didn't used to be on the old spec, it's coming in the new spec, so there's not many past paper questions on it yet, but we'll have a look at a past paper question in a while. Those are the three approximations that you need to memorise. So here are some examples from your booklet, which are on page 12. When theta is small, find an approximate value of. So let's start with question A. Well, earlier on we said that sine theta was approximately equal to theta. So using the same logic, sine of 2 theta is approximately equal to 2 theta. So we can change the sine of 2 theta into 2 theta. Then we can change tan of theta into a theta, because that was one of our approximations from earlier. Tan of theta is approximately equal to theta. And on the bottom is just a 2 theta, which we can leave as it is. So on the top we can simplify 2 theta plus theta is the same as 3 theta. And then this can be simplified because the thetas will cancel out. So we'll just end up with 3 over 2. In part B, we have got a cos 4 theta on the top. Now earlier on we said that cos theta was approximately equal to 1 minus theta squared over 2. Notice that it's not all over 2, just the theta squared over 2. So if we wanted to approximate cos of 4 theta, we could do 1 minus 4 theta squared over 2. So let's put that in, 1 minus 4 theta squared over 2. Then there's a takeaway 1 in the question. And then there's a giant fraction, and on the bottom there's a theta, and then a sine of 2 theta. Well, from what we said earlier on, sine of 2 theta is approximately equal to 2 theta. So let me finish my colour coding. I've changed cos 4 theta into this. And then I'm changing sine of 2 theta, I'll use a different colour. Sine of 2 theta is approximately 2 theta. So let's simplify. On the top, the 1 and the takeaway 1 are going to cancel each other out. Then I've got 4 theta, which I'm squaring, so that's going to become 16 theta squared. Dividing that by 2, so it becomes 8 theta squared, and it's negative. On the bottom, theta times 2 theta is 2 theta squared. The theta squares will cancel, and minus 8 divided by 2 is minus 4. Here are some more examples from your booklet, again on page 12. So in part A it says, show that when theta is small, sine of 5 theta plus tan of 2 theta minus cos of 2 theta is approximately equal to, and then we're given the answer to aim for. Okay, so let's use the highlighter. So I'm going to change the sine of 5 theta into a 5 theta. That's the approximation for sine. Tan is another easy one to do. Tan of 2 theta is approximately equal to 2 theta. The one that's a little bit more complicated to do is the cos. So cos of theta on its own was approximately 1 minus theta squared over 2. So I'll use that, but instead of theta, I'll do 2 theta. So I'm going to do 1 minus 2 theta squared over 2. I want to subtract all of that blue stuff. So that's my approximation for cos of 2 theta. And now I just need to simplify it. So from the yellow and the green, 5 theta plus 2 theta is 7 theta. Then I'm subtracting 1. And a minus times a minus is a plus. 2 theta squared is 4 theta squared divided by 2, which is 2 theta squared. And then if I just change the order around a little bit, you can see that it's the same as what we were aiming for. In part B, it says, hence states the approximate value of sine 5 theta plus tan 2 theta minus positive 2 theta for small values of theta. So what they want us to do in part B is they want us to go one step further, and they want us to make theta very, very small. Well, if we make theta very, very small, the smallest we could make theta would be 0. So let's allow theta to tend towards 0. Then 2 theta squared plus 7 theta minus 1 would tend towards minus 1, because that part would become 0. This part would also become 0. So we're just going to be left with minus 1. So if the angle is really small, so 0.0000 something, 0, then our answer is going to tend towards minus 1. So there's an exercise in your booklet on page 13, which I recommend now that you have a go through. Remember, the answers are all in your booklet as well. So press pause now on the PowerPoint to have a go at some of those questions. Finally then, I've got a past paper question here. This one's from 2018, and it says use small angle approximations to find the small negative root of this equation. Okay, so sine of x can be approximated to x. Cos of x can be approximated to 1 minus x squared over 2. So we can put those in. We've got to add them together, and we've got to put it equal to 0.5. So we're ending up now with a quadratic to solve. I would double everything just to get rid of that fraction. So 2x plus 2 minus x squared equals 1. Now I'm going to move everything onto one side. So if I move everything onto one side, I've got now 0 equals x squared minus 2x minus 1. And now I can solve that using the quadratic formula. I'm not going to use factorising because I don't think this one will factorise very easily. So I'm going to use the quadratic formula. So minus b plus or minus the square root b squared minus 4 times a times c all over 2a. Of course, if you've got the class whiz calculator, you can go into the equation solver and it will solve it for you, which I'm now going to do. So we end up with two answers for x. One of them is 1 plus root 2, which is approximately 2.4 to 1 decimal place. Or the other answer is 1 minus root 2, which is approximately minus 0.41. Now, going back to the question, they asked us for the negative root, so we've now got to make it clear to the examiner that even though there are two answers, we are going to choose one of them. They've asked us for the negative one, so the one they want is minus 0.41, or you could leave it as 1 minus root 2 if you wanted to. Either are correct. So that's all it is really for small angle approximations. It's only a tiny little topic. You won't find lots of past paper questions on it because it wasn't in the old spec exams. You might find some in the new spec exams. Here's the mark scheme of the question that we've just gone through. It's worth 3 marks, so you can see where the 3 different marks came from.